All right, welcome to 1.04. Here we're going to kind of solidify our understanding of vertical and horizontal asymptotes using limits. You might imagine that, for example, a vertical asymptote is much easier to sort of understand when you think about limits, right? Because you're approaching a certain value. And we'll obviously be using the strategies that we've learned in the past and kind of add to those a little bit as we go along. All right, so let's consider the function g of x here, and let's find both of the one-sided limits. Now, I want to just sort of recap some of the strategies that we've used in the past and how we might kind of figure out which strategies we want to use. The most efficient strategy for evaluating a limit is going to be saying, oh, it's continuous, let me plug in the value. Now, if it's not continuous, we need to then think about what can we do to the expression to maybe eliminate that problem spot. And here, of course, we have that situation where we wouldn't have a continuous function, and so we need to eliminate that problem spot. But here, there's just nothing. I mean, we would try and cancel out the denominator, but there's never going to be a way to factor 10x to get x minus 2, and so we're out of luck there. And so what we can think about is the kind of tried and true method that's always going to work, and that's using a table, making a table of values. And while it's not incredibly efficient, particularly when we're working with one-sided limits, it will be a little faster because we're only going in one direction. It's gonna work for us. It's just gonna take a little bit of time. So here, let's go ahead and make a table of values since the other two options aren't working. And of course, I left out graphing. And in general, we want to steer away from graphing because that's really only going to be efficient if we have a calculator handy, and we want to make sure we can do these without a calculator. So let's go ahead and create a table of values as we approach 2 from the left-hand side. So why don't you go ahead and do that, and then we'll kind of recap. So if we look at the table of values, starting with 1, and as we move closer to 2 from the left-hand side, g of x is going to get more and more negative, and it's going to get very, very negative. And so we can see that as we get closer and closer to 2, the values of g of x are approaching negative infinity. And this should make sense. Here's why. The numerator of our function is going to be getting closer and closer to what? Well, we near 2, we're getting closer, the numerator is getting closer and closer to 20, right? But our denominator is going to be getting closer and closer to 0. And so we can think about, right, as the denominator gets very, very, very small, but the numerator stays, it's getting closer and closer to 20, our values are going to be getting really, really, really massive. And in this case, since the numerator is going to be negative to the left of 2, then they're going to be getting massively negative, okay? So we would say that this is approaching negative infinity. Okay, so the limit as x approaches 2 from the left of g of x is going to be equal to negative infinity. All right, so now let's take a look at the limit as x approaches 2 from the right of g of x. And again, let's make a table here since all of the other options aren't really available to us. All right, so here we see something very similar. As we approach 2 from the right-hand side, starting with 3, we see that the value of g of x is getting very, very large. It's growing with what we say without bound, right? Just getting very huge. And we can see why this is by looking again at our function. We notice that the numerator is approaching 20 as we get closer to 2, and the denominator is getting closer to 0, right? And so we know that the smaller the denominator gets, it's just going to make our value really massive. And since x minus 2, this is going to be getting closer to 0, but it's going to be positive still, right? So 3 minus 2 is positive 1. 2 minus 1, 2.1 minus 2 is going to be positive 0.1. 2.01 minus 2 is going to be positive 0.01. So on and so forth. We see that these values are going to still be positive. And so they're going to get very massive, they're going to grow without bound, but in a positive manner. So this is getting closer and closer to positive infinity. So we say here that the limit as x approaches 2 from the right of g of x is equal to positive infinity. Now I want us to consider what that means about our function, and this is actually something that we've seen before. So if we were to graph this function, notice that as we moved closer and closer to 2 from the left, our function would be diving down towards negative infinity. And as we approach 2 from the right, our function would be shooting up towards positive infinity. And so this is what we call a vertical asymptote. So I'm going to sketch this graph very quickly. And here we can see, look, this is a rational function, has horizontal asymptote at 10, but the vertical asymptote is at 2. And the reason that is as we approach 2 from the left-hand side, the function is diving down towards negative infinity, and as we approach it from the right-hand side, the function is shooting up towards positive infinity. And this is actually how we define a vertical asymptote. And so here's the definition of a vertical asymptote. So the line x equals a is a vertical asymptote of a function f of x if the limit as x approaches a from the left of the function is plus or minus infinity, positive or negative infinity, or if the limit as x approaches a from the right of f of x is positive or negative infinity. Either one of these being true means that that line that goes through the value a that we were approaching is a vertical asymptote. Okay, so there are many different ways. In fact, there are 4 different ways, right? The limit as x approaches a from the left or from the right of the function can be either positive or negative infinity, and that tells you that for certain that the vertical line through that value a is a vertical asymptote. Okay? So we can use this to our advantage now when trying to figure out a vertical asymptote. We can use the limit. Alright, so considering g of x as the function 24x over x squared minus 9, determine the following. So go ahead and give this one a try on your own. You should be able to do just fine, and then we'll review the answers in just a few minutes. Okay, so certainly you could have made your way through this by creating a couple of tables here, and there's nothing wrong with that. But I want to walk us through a similar thought process to the first problem that we did, which will allow us to think about kind of the limit of the numerator and the limit of the denominator in a way that will make it very clear what the limit of the rational function is. So let's start with the limit from the right-hand side, and so I'm actually going to just go ahead and plug in our rational function. And the rational function we have here is 24x divided by x squared minus 9. Alright, so one thing to keep in mind is that if we're going to have a fraction that ends up being infinity, then we have to have a numerator that isn't 0, right? So it's important that the numerator isn't getting closer and closer to 0. If that's the case, right, we just have something that's undefined. But that's not the case here, right? 24x as we get closer and closer to 3 is getting closer and closer to 72, right? 24 times 3 is 72. So we know that the numerator isn't getting closer to 0, and so now we just look at the denominator. And what we want to consider is this. We know the denominator as we approach 3. When we plug in 3, it's going to be 0, right? But the question is, as we come in from the right-hand side, what type of values will we have here? And certainly we're going to have very small values because it's getting closer to 0. But there is a difference, right? It could be a negative or it could be a positive value. And so if you imagine, right, you have a positive numerator and your denominator can either be getting closer to 0 in a positive way or closer to 0 in a negative way, which means we're either going to be getting closer to positive infinity or negative infinity. And here you can see if I'm plugging in values to the right of 3, then I'm going to have values that are slightly bigger than 9. So I'm going to have positive values that eventually are getting closer to 0. which means that this is going to be approaching positive infinity. Now I can think pretty much the same way for the second one here, as I'm looking at the left hand limit from the negative side. And again, I want to consider what is happening to the numerator and the denominator as we approach from the left side. So the numerator is the same. Again, we can actually plug in 3 into the numerator and see that it's approaching 72. And now let's consider values just to the left of 3 and think about what that will mean for our denominator. So imagine a value like 2.9, right? 2.9 squared is less than 3 squared. So this denominator is going to be negative. And so since we know it's approaching 0, and we know that, any value less than 3 squared is going to be less than 9, we know that our denominator is going to be approaching 0 in a negative fashion. And so we can tell very clearly that this limit is going to be negative infinity. So now we move on to the two-sided limit, and this one should be very quick. Remember, for a two-sided limit to exist, we have to have both the left side limit and the right side limit equal each other, and that is not the case here. So the limit as x approaches 3 of g of x does not exist, right? And so last but not least, we want to know if x equals 3, the line x equals 3 is a vertical asymptote for g of x. And if we just think back a couple minutes ago to how we defined asymptotes, vertical asymptotes, either the left or the right hand limit had to be equal to either positive infinity or negative infinity. And so we overqualify, so to speak. We have more than one of those match up and hit for us. So this definitely is a vertical asymptote for g of x. Okay, so that was how we can use limits to really understand vertical asymptotes. And remember, with rational functions, we're not only concerned about vertical asymptotes, but also about the end behavior. In other words, what happens as we move way out to the right or way to the left? In other words, what happens as our x values get closer to positive infinity or negative infinity? And limits can make this really, really clear, right? They can really help us understand end behavior and define the horizontal asymptote. So why don't you go ahead and give this a try, see if you can remember some of the moves that we made when discussing horizontal asymptotes, and it might be very helpful in evaluating these limits as well. Alright, so let's start with the limit as x approaches positive infinity. And so just to get a kind of conceptual understanding of this, right, we're looking at this graph of g of x in our heads, so to speak, and we want to know what is it going to be doing as we just move way out to the right. Okay, so let's rewrite this. Limit as x approaches infinity of 10x over x minus 2. Okay, so let's just first think about the first strategy that we always want to use when evaluating limits, and that is to see if we can plug in the value. Now, notice that this function here, this is continuous everywhere except when x is 2. And, well, this isn't x equals 2, so, maybe we can think about plugging it in, right? Well, that's kind of a problem, because 10 times infinity is infinity, and infinity minus 2 is infinity, right? So plugging in infinity isn't quite going to get it done for us. But we want to take advantage of something that you may remember, and that is, if we have some value, some number, like a constant value, say 2, for example, and we divide it by infinity, well, that's 0, right? Any number divided by infinity is 0. And so we actually have an opportunity to cancel the x's from everywhere except have it dividing by 2. Dividing the 2 here. And the way that we can do that is since we have 10 times x in the numerator and we have an x to the first power here in the denominator. If we just multiply everything by 1 over x, we'll end up with exactly the situation I just described. So what we want to do is we want to multiply the numerator by 1 over x. We want to multiply the denominator by 1 over x. It isn't something that we do very often, but it happens to be really, really helpful here. And so we can rewrite this statement. Don't forget to rewrite the limit as x approaches infinity. And let's just think about what the numerator is going to be. So we have 10x times 1 over x. So that's going to be 10x over x, which is 10. And in the denominator, I have to distribute, and so I multiply 1 over x times x, and that's x over x, which is 1, minus 2 over x. And what we have here is something that when I plug in infinity is actually something I can get a hold of, right? I can actually understand what that is, and that's because 2 over infinity, that's going to be 0. Okay? And so what I'm left with is that the limit as x approaches infinity of this right here is 10 over 1 minus 0, which is 10. Okay? Let's go ahead and try this on the limit as x approaches negative infinity. And I encourage you to go ahead and pause and try this on your own if you want a little extra practice. It would be a good idea. Okay, so here I'm going to rewrite this as the limit as x approaches negative infinity of 10x over x minus 2. And here I'm going to apply that same trick that I applied previously, which is to multiply by 1 over x. And what that'll allow me to do is rewrite my limit, except this time I'll have something that I can actually interpret when I plug negative infinity into it. And here's why. Imagine I take 2 and divide it by negative infinity. Well, that again is 0. And so what I'm left with is that the limit is 10 over 1 minus 0, which is, of course, 10. And so we want to think about what this means, right? Well, what this is telling us is that as you move infinitely far to the right, your function is going to be getting closer and closer to 10. And as you move infinitely far to the left, your function is going to be getting closer and closer to 10 again. And so if you remember that we graphed the function when we saw this, this function earlier, and you notice that I had a horizontal asymptote there. We already found that the vertical asymptote was at 2, so let's go ahead and sketch that graph one more time so we can clearly see both aspects. So again, I know previously that there is a vertical asymptote at 2, and now I also know that there is a horizontal asymptote at 10, which is to say, as my function moves further and further to the right, the value of the y value is getting closer and closer to 10, and as it moves further and further to the left, the value of my function is getting closer and closer to 10 as well. And there you have it. And so this allows us to define the horizontal asymptote in terms of a limit as well. And so we can say that the line y equals b, horizontal line goes through the y-axis, is a horizontal asymptote of the function f of x if the limit as x approaches infinity of the function f of x is equal to that value b, or if the limit as x approaches negative infinity of the function f of x is equal to that value b. And so what this tells us, look, is if we want to know whether something's what the horizontal asymptote is, we can look at the limit either as x approaches positive or negative infinity of this function, and the value that we get for that limit will be the horizontal asymptote, will be the value of the line y equals b for that horizontal asymptote. Okay, so now we can use limits to define both horizontal and vertical asymptotes. So I have a couple questions for you to take a look at, and we can debrief them when we meet again.